Hi there, we are back with Chapter 11, Section 11.10, Taylor series and Maclaurin series. So let's again use the use of a Taylor coefficient to find a Maclaurin series for f of x equal to e to the x. So remember, a Maclaurin series is one that is centered about a equal to 0. So we're going to build a table here of n values, followed by the nth derivative of x, followed by the nth derivative evaluated at a, and here a is equal to 0, and then we will come up with a formula for, or a value for each of the Taylor coefficients, and c sub n is the nth derivative evaluated at a over n factorial. So in this case, it's going to be the nth derivative evaluated at 0 over n factorial. So we're going to make a couple of these and hopefully establish a pattern, and then we will form a series around a equal to 0 for e to the x. Alright, so when n is equal to 0, we do not take the derivative, so we just have f of x equal to e to the x. When we evaluate f at 0, we get e to the 0, which is 1. And c sub 0 is now going to be 1 over 0 factorial. And we'll leave it like that until we see if we're able to establish a pattern. So now let's proceed with n equal to 1. So we're going to take the first derivative of e to the x, and the derivative is e to the x. We're going to evaluate at 0, which again we get e to the 0, which is 1. And our c sub 1 now is going to be 1 over 1 factorial. N equal to 2, we'll take the second derivative, and the second derivative of e to the x is still e to the x. And evaluating at 0, we end up with 1, and our c sub 2 is 1 over 2 factorial. And proceeding, I see that we are going to easily be able to establish a pattern. The third derivative evaluated at 0 is e to the 0, which is still 1, and our c sub 3 is 1 over 3 factorial. So we could repeat, but we do establish a pattern and see that c sub n is going to be 1 over n factorial for any n. So our Maclaurin series for e to the x is going to be a c sub n x to the n for n equals 0 to infinity, and we found our c sub n, and that's going to be 1 over n factorial times x to the n. Good. And we saw in a previous section the by the ratio test. The limit as n goes to infinity of a sub n plus 1 over a sub n equal to the limit as n goes to infinity of x to the n plus 1 over n plus 1 factorial times the reciprocal of a sub n, which would be n factorial over x to the n. If we are to cross-cancel our common factors, n factorial cancels with n plus 1 factorial to leave a factor of n plus 1 left over. And that is going to 0. And 0 is always going to be less than 1 for all x. So our conclusion here is that our radius of convergence is equal to infinity, and our interval of convergence is all of r, or negative infinity to positive infinity. Good. So that is e to the x, a Maclaurin series for that. So in this example, the sequence of Taylor polynomials are as follows. T sub 0 is equal to 1. That is the sum of the first 1 terms. T sub 1 of x is 1 plus x, and T sub 2 of x is 1 plus x squared over 2 factorial. And remember, these are sequences of Taylor polynomials. This is the sequence of partial sums. And just to be clear, this would be the Taylor polynomial of order 3 or degree 3. Good. And when we graph our Taylor polynomials against the function, and we're doing this around a equal to 0, we see that each particular graph on its interval of convergence actually becomes e to the x over